Bonding theory and hybridized orbitals principles summary. Hybridized and valence bond theory. Valence bond theory describes a covalent bond as the overlap of half-filled atomic orbitals, each containing a single electron, that yield a pair of electrons shared between the two bonded atoms. On the left of the diagram, we have atom A with a positive spin up. On the right side of the diagram, we have B with a positive spin up. They meet in the middle to form a spin up and spin down bonding pair with overlap. According to valence bond theory, a covalent bond results when two conditions are met. 1. An orbital on one atom overlaps with an orbital on a second atom. And 2. The single electrons in each orbital combine to form an electron pair. The overlapping of electrons to form covalent bonds forms hybridized orbitals, which is a blend of the previous independent orbitals. Hybridization. Hybridization is mixing of two or more atomic orbitals to form a new set of hybridized orbitals. 1. There is mixing of at least two non-equivalent atomic orbitals, for example, S and P. Hybridized orbitals have very different shape from original atomic orbitals. 2. The number of hybridized orbitals is equal to the number of pure atomic orbitals used in the hybridization process. 3. Covalent bonds are formed by A. Overlap of hybridized orbitals with atomic orbitals. B. Overlap of hybridized orbitals with other hybridized orbitals. Essentially, hybridization takes the electronic configuration of one atom and hybridizes it with another atom. Lennard-Jones theory. Lennard-Jones theory holds that two spin-up electrons will travel down a common path where one will flip to a spin 1/2 down to form a stable bond at the lowest energy position on the energy curve, where there is an ideal internuclear distance for that bond formation. The deeper the well, the stronger the interaction between the two particles. In other words, more stable bonds. The horizontal distance from the y-axis to the well bottom is the bond length. The vertical height from the well bottom to the x-axis is the potential energy, or bond energy. Orbital overlap. Orbital overlap can occur where there is S to S overlap, and when this occurs, sigma bonds are formed. Orbital overlap can also occur when there is S to P overlap. In this case, S and P can form sigma bonds. P to P overlap can occur in a head-to-head fashion where they meet on a horizontal line to form single bonds for head-to-head. PP overlap can also occur by side to side where the two P orbitals stand vertically and approach each other and form an overlap, which is called a pi bond for a side-by-side bonding.